Let's do some example problems of the technique completing the square. This technique is often used to solve quadratic equations, and that's what we're going to be doing here. It's also used to do some other stuff in mathematics, so it's a really important technique to sort of have in mind. Completing the square has some steps. The first step, the most important thing, is really making sure that this coefficient of x squared, or whatever your variable is, whatever that squared variable is, it should have a 1 in front of it. And notice that it does here. There's already a 1 in front, so that's okay. That's what I want. The second thing then I try to do is get all the stuff with x on one side and the constant on the other. Well, that's already been accomplished here, so we don't have to worry about that. The next thing is I have to sort of get this special number, I sometimes think of it as, or secret number that I'm going to add to both sides so that it factors nicely. The way that comes about, I always look at the linear term where I have x to the first power, and I look at what's with that x, and that's this number -6. And so I'm going to take half of that number and then square it. Well, remember, 1/2 of something will be 1/2 times that something. So I get 1/2 times -6, and then I take half of that and square it. So that's going to be -3 squared, which is going to be 9. So I'm going to add 9 to both sides. Now, just as a note, when you're doing these problems, this negative that's here in front of the 6 really ends up not being important for finding this special number. If I would have come up here and just said, what's 1/2 of 6 squared? Well, then I would get 3 squared instead of -3 squared, but it would still be 9. This special number is going to be 9 no matter what. So I'm going to get x squared minus 6x plus 9 equals -5 plus 9. The next part then is when I look at this trinomial here, 3 terms, trinomial, if I've completed the square correctly, I should be able to factor this as something times itself. So I break it into 2 sets of parentheses. Let's see, -5 plus 9, that's equal to +4. The x squared has to be x and x. The 9 comes back here. Where did it come from? It came from 3 times 3. But then to get -6x in the middle here, these 3's are both going to have to be negative. And so I can write this as x minus 3 quantity squared equals 4. And now I can solve this problem by taking the square root of both sides. That's that square root property. So we just get x minus 3. When I take the square root, when I decide to take the square root, I have to throw in plus or minus. So the square root of 4 is 2. When I add 3 to both sides here, I get x equals 3 plus or minus 2, right? That 3 could go at the end. You could have plus or minus 2 plus 3, but we use the commutative property usually to write it in front instead of at the end. Now, in a case like this, where you've got a definite number that's being added or subtracted, we usually take the step of actually breaking this into the 2 separate parts. So if I do the plus, I get 3 plus 2. If I do the minus, I get 3 minus 2. And so my solutions are x equals 5 and x equals 1. So I get 2 definite solutions. When I end up with nice solutions like this that don't involve square roots, that means the original equation could have been solved by factoring. So I could have taken this equation over here and had x squared minus 6x. I'd add 5 to both sides. And then I could factor this as x minus 5 times x minus 1. So then I'd get x minus 5 equals 0, or x minus 1 equals 0. I would have had the solutions of x equals 5 and x equals 1 the same you know, these two solutions here are the same solutions I got here. So if you get nice solutions, that meant factoring would have worked, but maybe we didn't realize that at the beginning of this problem. Okay, so in this particular problem, again, completing the square we're going to use, we see that there is already a 1 in front of my squared variable, so I'm not going to have to worry about that. In this case, though, this minus 7, I want the stuff with r on one side and any constant on the other. So this minus 7 I'm going to have to move. So I'm going to add 7 to both sides. That's going to give me r squared plus 10r equals 7. Okay, so now I can find this special number. I look at the coefficient of my linear term, that's my r to the first power. That coefficient is 10, so I'm going to have to take 1/2 of 10. 1/2 of 10, that's 1/2 times 10, and I'm going to have to square that. So that's going to be 5 squared, which is going to be 25, and I'm going to add that to both sides of the equation. So plus 25, 7 plus 25. And now if I've done everything correctly, this should factor as the same thing twice. R squared is r times r. The 25 came from 5 squared, so 5 times 5. And to get this positive 10r, they're both going to have to be plus. 7 plus 25 is 32. So this is a perfect square. I have the same thing twice. And I solve that then by using the square root property. I just take the square root of both sides. When you decide to take the square root, you have to throw in plus or minus. So we're going to get plus or minus the square root of 32. In this case, I can't take the square root of 32 exactly. If it was the square root of 36, I'd be okay, but not square root of 32. But I can simplify this. 16 is a perfect square that goes into 32. So I can say that's the square root of 16 times the square root of 2. Square root of 16 is 4. Don't take the square root again, right? The square root of 16, once I take the square root and go from 16 to 4, this radical did its job, so it goes away. This radical, I can't take the square root of 2, so I have to leave it. Next, then, I need to get the r by itself, so I'm going to subtract 5. And so I'm going to get r equals, the negative 5 can either go in the front or the end. I'm going to write it in the front. So my solutions are negative 5 plus 4 square root of 2 and negative 5 minus 4 square root of 2. Remember, I can't combine these together. I can't say negative 5 plus 4 is negative 1. I can't say negative 5 minus 4 is negative 9. I just have to leave the solutions that way. Okay, so this problem. Again, I've got a 1 in front, so that's good. That works out fine. But I need all the x stuff on one side and the other stuff on the other side. So, you know, I might start here. I want all the x stuff over on the left, maybe, with the x squared. So I'm going to subtract 12x from both sides. But then I don't want the 40 with that stuff. I want to get rid of the 40. So I'm going to subtract 40 from both sides. So this is just getting it in this nice form, right? I want the x stuff on one side, anything else on the other side. And you can write down as much or as little as you want when you're doing this. Then I find this special number, right? 1/2 the coefficient of the linear term of my x term here. So that's 1/2 of negative 12. Remember that negative isn't really important because it's going to get squared anyway. So I'm going to take 1/2 of, that's times 12, and then I'm going to square that. So that's going to give me 6 squared, which is going to be 36. So I'm going to add 36 to both sides. Alright, now if I've done that correctly, this should factor as something squared. X squared is x times x. The 36 came from 6 squared, so I'm going to think 6 times 6. To make that a negative 12 in the middle, those are both going to have to be minuses. And then negative 40 plus 36, there's more negative than positive, so that's going to be negative. Now, that's okay. I'm eventually going to take a square root, and I'm going to get the square root of a negative, but that's just going to involve I. So here I do have x minus 6 squared equals negative 4. And then I'm just going to take the square root of both sides. So the square root of something squared goes away. When you take the square root, you have to throw in plus or minus. And now the square root of a negative, well, that's just going to involve I. And of course, the square root of 4 is 2. So I would write 2i. And then I'm going to add 6 to both sides. So my solutions, I'm going to get 6 plus 2i and 6 minus 2i. And as I've been saying all the way along here, you cannot put the 6 and the 2 together. This has an I, this does not, so they're not like terms. Now these first three were set up so they were pretty easy to use completing the square with. This last example is a little bit more complicated because when I look at this term, you know, that needs to be a 1. And so what I'm going to do at the very beginning is I'm going to divide by whatever I need to make that happen. So I'm going to get 2x squared over 2 minus 9x over 2 plus 9 over 2, and 0 over anything else is still 0. So these 2's cancel out. That was the point. So I'm going to get x squared minus 9 halves x plus 9 halves equals 0. Remember, this really is over 1, so it really is the same thing. 9 times x is the 9x, 2 times 1 is 2, and the negative is still there. All right, well, where this gets a little more complicated is now when I find this special number. Because I have to take half the coefficient of my linear term. My linear term is the x to the first. That means I have to take half of 9 halves. This is where thinking of a half of something as a half times something is really important. So I'm going to take 1/2 of, 1/2 times the 9 halves, and then I'm going to square it. So 1 times 9 is 9, 2 times 2 is 4, and that's still squared. And so my special number I'm going to add to both sides is 81 over 16. Now, I'm sorry about that. That's just going to be what we have to have happen. Oh, I forgot one other thing here, though. That's still good. We're going to need that. Completing the square, I wanted a 1 here, but I want to get rid of this, right? I want to leave the x stuff on one side and move the constant to the other side. So I'm going to subtract 9 halves from both sides. That's going to leave me x squared minus 9 halves x equals negative 9 halves. And now I'm going to add this special number to both sides. So x squared minus 9 halves x plus 81, oops, let me do that a different color. plus 81 over 16 equals negative 9 halves plus 81 over 16. And now over here, I'm going to try to factor this as the same thing twice. The x is easy. X times x is x squared. Now you may say, oh, these fractions, how am I going to do this? This is going to be horrible. It's not really that bad. Where did this 81 over 16 come from? It came from 9/4 squared. So that's what I'm going to put here, 9/4 and 9/4. So now notice x times x is x squared, 9 times 9 is 81, 4 times 4 is 16. Does that middle part still come out? Well, to make it negative, these are both going to have to be minus. Does it really work? Well, outer, I would get negative 9 over 4. Inner, I would get negative 9 over 4. They already have a common denominator. So I'd put the negative 9 and the negative 9 together. That would give me negative 18 over 4. But when I divide top and bottom, then I get the negative 9 halves, which is what I wanted. So this does work. Over here, I'm going to want to combine these together, but I'm going to need a common denominator. So can I turn the 2 into 16? Sure. I just need to multiply by 8. But whatever I do to the bottom, I have to do to the top. So I'm going to get x minus 9/4 squared equals negative 72 over 16 plus 81 over 16. So when I put those together, we get negative 72 plus 81. That would be 81 minus 72. That ends up being 9 over 16. So then I can take the square root of both sides. So square root of 9 is 3, square root of 16 is 4. So I'm going to get x equals 9/4 plus or minus 3/4. Since those are exact fractions, I can split this up. So one of my solutions is x equals 3. The other would be 9/4 minus 3/4. So that would be 6 over 4. I can divide top and bottom by 2, and I get 3 halves. So those would be my two solutions. Now, this problem was much more complicated than the other three. I'm never myself personally going to force you to use completing the square to solve this type of an equation. Most people, when faced with solving this type of an equation, are going to use the other technique that we've talked about called the quadratic formula. But I just wanted you to see the worst case that you can sort of have, and that's this problem. But don't worry too much. I'm not going to force you to use this technique on a problem like this. I just think it's important that you've seen it.